So now we turn to the actual Mplus inputs, and we'll take a look at the results of the analysis using these different approaches. Slide 16 shows a useful summary of the different steps, and this is then geared towards handling missing data on the covariates. And we're going to talk about two stages of analysis: the measurement model stage and the final analysis stage. I'm using the word stage instead of steps here, not to mix it up with 3-step and 2-step, by keeping it in two parts here. So first stage is the measurement model analysis, and input specifications then that we should pay attention to include the use variables list, which is then the U1 through U12 latent class indicators. And on the right, in the right column here, you have the variables that are saved in the analysis when you add the save data command. So when you have the save data command, you automatically save the use variable, the variables on the use variable list. Now in the first stage, we also want to ask for the auxiliary option for saving variables for the final stage. So the variables that we would save then are the covariates and the distal outcomes. Furthermore, you want to use the save data command to save C probabilities, which are used for 3-step. That saves the C probabilities for the 9 combinations of classes, 3 times 3. And we also have N1 and N2, which are the words we used for the most likely classes for time point 1 and time point 2. We use the letter N for referring to a nominal variable. The save data command you can also use to save BCH weights for the BCH multi-step approach, and that saves the weights, the BCH weights for the 9 class combinations in the saved data. And then you also want to use S values, which is for S2-step, and that's not variables saved, but they will come out in the output from the stage A measurement model analysis, and you will then be able to copy those into the second stage, which is the final analysis, including multiple imputation first of all for the X's with missing data, and then an analysis of the full model. Full model meaning that we add the covariates and the distal outcomes. And we're going to use data imputation for missing on X. Can be replaced by integration, but we're going to focus on imputation for missing on X here. And then in the final analysis here, stage B, we have the alternatives, 3-step, BCH, and 2-step. And the way you've set it up then here means that you can easily do all 3 if you want to. And let's take a look at the difference between the 3 approaches. For 3-step, the use variable list includes the most likely classes designation, N1 and N2 for the C1 and C2 latent class variables, and then the covariates and distal outcomes. For BCH, the use variable list does not include N1 and N2, but X1 and Y3, X1 to X3 and Y1 to Y3. And for 2-step, the use variable list includes the measurement model indicators, U1 through U12, because we fixed those measurement parameters, as well as the covariates and the distal outcomes. For 3-step, then, we have to also look at the logits from stage A and copy those logits into the last step, manually added. BCH, however, has the convenience that you get the BCH weights in the first step, in the stage A rather, and in the stage B analysis, you only have to specify that this training option, W1 through W9, in parentheses BCH. So that's the most convenient approach for taking these 2 stages of analysis. For two-step, you have to copy over the S values from stage A and manually adding them to the input for the stage B analysis, and change the asterisks to @ to fix those values, as we discussed in detail in Webtalk 8. So there you have a summary of it. So let's take a look at the details of the input then for stage A on slide 17. So here we save the information we need for the final analysis. So we have this data set, LTA distal N2K, same data set as we use for the regular LTA analysis. And here's a list of variables in that data set. And we're going to use the latent class indicators U1 through U12. And we're going to have 3 classes for each time point and declare those U variables as categorical. And here's what we need to do. We need to add the auxiliary option to save X's and Y's for the last step. And then we do a mixture analysis with a sufficient number of starts. And continuing on the next slide, then we have the model parts, the overall model, model C1 and model C2. And the overall part, then we don't say C2 on C1, but leave that at 0, as we have discussed earlier. And for model C1, we have the 3 classes of C1 with labels to be able to hold equalities across time for the same indicators at time point 2. And then we save the data, use the save data command to save the C probabilities for 3-step, BCH weights for BCH, and we save them in the stage A.dat, the new data set. And we also ask for S values, so we get those ready if we want to try 2-step analysis. And here's what we get: latent class counts and proportions for each variable, C1 and C2. And you get a 0.42 class, 27, 28, 298 here, and a little bit different at the second time point, because there are transitions from C1 to C2 that creates a different marginal distribution for C2. So that's all right. Now we may want to reorder the classes. Typically we want to have the biggest class last, because that's the class we compare to. So for ease of interpretation, we may want to put that normative class last. It doesn't matter to the, doesn't change the analysis results, except maybe more easily interpretable. So we can reorder the classes, and we want to do that in this first stage. So based on C1 here, we want to have the lowest class first, say. So 2 comes first, and then the second lowest comes next, so 3, and the biggest class we want to have last. And we want to do the same thing for C2. So 231 bar 231. So reordering of the classes is easily done. You have the same input here as before, except now you have opt seed. You take the optimal seed from the output in the first run, and here is the same input as before, except you have added then the S values reordering. All right, slide 22 then. Let's take a look at something here which might be of interest. I'm specifying the latent class indicator probabilities. You know, we talked about a high class, a low high class, and a low class. And that was from regular LTA, where we do specify C on C, so to speak, C2 on C1. And comparing that then to the first step, or stage A, of the multi-step analysis, where we have no C on C, you see that in this case, the 2 solutions for the measurement model are very much the same, very similar: 794, 793, 786, 787, etc. And now in this case they're similar because the data are generated to fit the model a model exactly like this, whereas in real data you may have a discrepancy between these two. This analysis on the right here is like analyzing each time point separately, whereas this analysis on the left looks at the joint analysis of both time points, and they may come out differently. For instance, if you have some correlations across time between indicators that are not accounted for by the regression of C on C. So you may want to keep an eye on that in your real analysis. Now, stage B then, on slide 23, what does that do? Okay, so we have the last step of 3-step here first. I'm going to do all three methods, 3-step, BCH, and 2-step. And it's based on the reordering of the classes. So stage A data has been saved in this reordered run, where we have the biggest class last. And here is the variable list that comes out of the stage A output. So the variables in stage A are listed at the end of that stage A run. And since it's 3-step, we're going to have the use variable list that includes these nominal variables, most likely class variables for C1 and C2, and then the covariates and the distals. And the categorical variables here then are Y1 and Y2. Y3 was continuous. And nominal is what we use for N1 and N2. And in stage A, the missing data flag is no longer 999, but it's asterisk. Now we're going to do the data imputation step here within this stage B analysis. So we do data imputation for the axis, and I'll describe that in some detail in Webtalk 8. But essentially, here's how it works. You have a names list. That's a set of variables that you use to inform about the imputation. So they carry information that's useful in imputing. And what do we impute? We impute x1 and x2, the two missing x's. So we specify what kind of variables they are, categorical for U1, U12, and for x1, and for y1 and y2. And we impute x1 and x1 is imputed as categorical, in this case binary. So here's the imputation approach that actually does take into account that x1 is binary. Again, I talk more about that in Webtalk 8. And we're going to impute 100 data sets. I'm going to draw 100 plausible values imputation for to get 100 data sets which have observed information on x1 and x2 by imputation. And we're going to save that as imputed asterisk.dat, so a list of data sets. And this imputation is done by Bayesian analysis. So we have the concept of thinning, that is not saving every iteration in the Bayes analysis, but skipping to make observations more independent. And we do thinning equals 100, that may be more than we need. Anyway, so we do mixture analysis then on these data, and although we use Bayes here for imputation, our analysis estimator is maximum likelihood. And since it's the last stage, last step, we use starts equals 0. So on slide 24 then, the last step of 3-step is as follows. You have then C2 on C1 here, and you have C1 through C2 on the covariates, and Y1 through Y3 on the covariates as well. And note then that in this case, at this stage, there's no missing on X after imputation. So they are treated as regular observed covariates that we condition on in the regression. No need to bring them into the model to handle the missing data, because there's no missing data on them, on the X's, after the imputation stage shown on the previous slide. I shouldn't call it stage, but after the imputation within stage B. So one analysis here that does imputation and mixture modeling in one single run. And then you have model C1 and model C2, where, because it's three-step, we fix these loadeds. These loadeds come from the stage A analysis that we copy over like this and fix them. And you can, if you want, add Tech 8 in the output, which shows you the base imputation iterations. Usually they come out okay and you don't have to worry about them. Now these loaded values, like I said, they are found for each latent class variable in stage A. So each latent class variable, C1 and C2, have these fixed loadeds. On slide 25, we turn to using the BCH method in the stage B, that is the last step, based on that reordering we did in the first stage, stage A. All right, so we still use the stage A data set, where these variables in the data. And now the use variable list does not include N1 and N2, but only the X's and the Y's. And declare the two Y's as categorical here. And now we add training, the training option, BCH. We have the same data imputation statement as for three-step. And the analysis by ML here is the same, except we don't have to bother with the fixed loadeds. All we do is specify the overall model as we did for three-step, and then model C2. We don't have to bother with model C1 because we have the training weights. And all we have to do is to say that the distal outcomes vary as a function of C2 alone here. So the thresholds and means are mentioned in each of the three C2 classes to match the picture, the figure of the model, where C2 influences the distal outcomes, but C1 does not. The X's, again, they come in the regressions here. And once again, there's no missing on them because we've already done imputation. All right, slide 26 then. What about two-step in stage B? All right, the stage A data is the same. Alternatively, two-step can use the original data since most likely class and weights are not needed, so we don't have to save that extra stage A that data set if you don't want to. So the use variables then are including the latent class indicators, because that's the measurement model part that we want to fix the parameters of using two-step, and then the X's and the Y's. So we include on the categorical list then the U variables as well, in addition to Y1 and Y2. Data imputation is the same as before. Mixture modeling is the same. Starts equals 0 because this is the last step. And two-step then continues here with C2 on C1 and C on X and Y on X. And in addition then now we have to use model C1, fixing the measurement parameters here using ampersand, having changed the asterisk to ampersand by copying the S value output in the first stage and changing the asterisk to ampersand. And same for C1 class 2 and 3, and on the next slide 28 for model C2, fixing those measurement parameter values. And again for model C2 we specify the thresholds and means for the Y's, because C2 is the only variable that influences the distal outcomes. So that's pretty straightforward. Again, least amount of work is required by BCH. And however, BCH doesn't always work, so we have to be aware of the other methods. Slide 29 gives the latent transition analysis class probabilities for the different approaches. As a comparison, we also give the class probabilities for the regular LTA, and we can compare that to the stage A of the multi-step approach. And to remind you, the regular LTA does allow for C2 on C1 regression, whereas stage A of the multi-step approach does not. And you see that in this case, the differences are very small between those two approaches. What we really want to focus on, though, is the difference between the stage A class probabilities and that are obtained from what we call the measurement model, and the multi-step methods, the three multi-step methods in stage B that add covariates and distal outcomes. And we see that we have fairly good control, or very good control, of the class probabilities between the first and the last stages in all cases. In fact, for the BCH approach, it's right on target, apart from this little difference here. And very close values, and here exactly the same as stage A. Two-step is also very, very close. So that's something you may want to check in your real data analysis. Slide 30 shows the LTA results for BCH. You have the class probabilities up at the top, but that we looked at before. And here I'm presenting also the estimated, some of the estimated quantities in the output. And I distinguish between four different parts of the output: the influence of X on C2, I'm ignoring X on C1, the influence of X on the Y's, and I'm only looking at Y1 and Y3, the influence of C1 on C2, and the influence of C2 on Y. So where you find these pieces of output in the Mplus run that you do is described in Webtalk 8 in detail. Now, I have this for both BCH and for, on the next slide, for two-step, and you will find that the results are fairly similar. So for instance, if you look at the Y1 odds ratios, influence of X on Y, 1.806, etc. If you go back to slide 30, 1.885, 578, 502, back to slide 31, fairly close. In fact, all the numbers are very close to each other across the two methods. I have not presented three-step here. And the asterisk, the significance, the estimates that are significant are the same except for one. This influence of X3 on the C2 class 2 odds ratio is significant here for two-step, but not for BCH. It's also not significant for three-step. So the significance for two-step is therefore slightly suspect. And that's perhaps, although this is one observation, one data set, one replication in the Monte Carlo study, may be indicative of the fact that the two-step standard errors are slightly underestimated due to not taking into account the random variation in the measurement parameters. Usually doesn't make much of a difference, and here actually the confidence intervals are very similar. It just slips over into significance for two-step, whereas it was not for BCH nor for three-step.